We are going to go through the Chapter 1 test review a little bit. I am going to skip around in the terms of questions just so that we're able to cover some of the stuff that is the most pressing. This is one that tends to get many students. We're looking at the fact that gravity causes objects to be attracted to one another. This attraction keeps our feet firmly planted on the ground and causes the moon to orbit the Earth. That force is represented through this equation. We're given the fact that sort of what everything is going to be measured in. We want to know what are the units for G. In order to do that, we're going to first solve the equation for G. So we see the fact that force is equal to G m1 m2 over r squared. And we're going to multiply both sides by r squared. And when we do that, this r squared is going to be multiplied by f. R squared and r squared cancel. So I do get r squared f is equal to G times m1 m2. Again, our ultimate goal is to get G by itself. So we're going to divide both sides by those masses. This one cancels with this one, and so on and so forth. So we do get the fact that our G is going to equal our force times our r squared over those two masses. Now it's important to go ahead and plug in what the units for each of these things are. You were given those in the problem. We are looking at the fact that the SI units for force are this, units of mass for kilogram or mass or kilograms, and the units of distance are m. So this is what we are plugging in for these values. So I still got G, and my force I'm going to replace with its units. So that's going to be kilograms times meters per second squared. My R is a distance, and that's going to be mass, and that term is squared, so that unit is squared. And then I have M1 and M2. Those are both measured in kilograms. Right? So you can go ahead and check your answer since this was multiple choice to see if any of these match this, and not quite. So we do need to go ahead and simplify this. I am going to do some rearranging just so that you can see this. Because this term here is divided, we are able to pull that into the denominator. So see if my computer wants to cooperate. All right. So this can be rewritten as I'm going to move this over to the side so I can see what I'm doing. Kg times mass squared, or not mass, forgive me, meters, kg times meters squared over second squared times kilograms. So now you're a little bit able to see where things are going to cancel, and we are going to have some cancellation. We do have double up sets of kilograms, so this is going to cancel with this. These terms can combine. So when we do combine those, I get mass cubed over kilograms times second squared. Right? It doesn't matter which order you put those in because multiplication is commutative. So this is what we are interested in here. So we're going to see if that matches anything we have over here. Why, yes, it does. So that tells us that this is my answer. So this is that process. Show your work because it is going to be how you are best able to get full credit. We are looking at something similar here. We want to look at what is the units for E, all right? We're looking for the units of energy. If we're given the fact that the units of speed are meters per second, and we are looking at the fact that we have M as mass, and we just learned the fact that mass is in kilograms. We can see the fact that E, whoops, I selected a new pen. E is equal to mc squared. This is a speed, this is a mass. So E is equal to kilograms times meters per second, and that term is squared. We do need to distribute that term, that square through that equation. So E is equal to kilograms times meters squared over seconds squared. And that is this answer right here. Right, so we didn't mean to rearrange this one, but that is what that looks like. So this is about converting some units. We want to sort of look at some things. The average height of an adult is about 5.5 feet. So as a result, you can sort of look at that in centimeters. So that was just sort of a approximation one. The same thing is going on for the mass. So 1 pound is about half a kilogram if the average person is about 100 pounds, they're going to probably be double that. We are more interested in significant figures. We want to know which of these choices signify correct rounding. If we take a look at some of our options, we have to look at first, what is our number? So if we round this to 4 sig figs, we have 1, 2, 3, 4. This number, if I look at what's behind it, has to round. So this is wrong, right? That is not incorrect sig figs. If I want to round to 3 sig figs, 1, 2, 3, the number after that doesn't cause it to round up, so that's good. Bam. This is 1, 2, 3, 4, 5, 6. 6 sig figs. Zoom in a little bit easier so we can see. 6 sig figs. 1, 2, 3, 4, 5, 6. The number after it doesn't cause it to round up. So that is also good. Right? So this is incorrectly rounded. Right. If we take a look at this one, we're still looking at the same idea. This is 4 sig figs. 1, 2, 3, 4. That's not going to cause it to round up, so that's good. This is 2 sig figs, not going to count. Yeah, excuse me, not going to cause it to round up, so that's good. Oops. And then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That 3 has a 6 after it, so that is going to round up, and we did round up. We are good. So all of these options are correct. There are different levels of precision. We rounded correctly. All right, just taking a look at how many significant figures you should get. I feel like you guys can handle this one on your own. So this one is just weirdly worded. So what we're doing here is we're converting this number into scientific notation. If we go ahead and put this in scientific notation, it's important to know what are the rules of scientific notation. The scientific notation is always 1 digit, the decimal point, and the rest of your digits. So 2.9979. We don't need all the rest of the zeros in this particular case because they don't contribute anything. This is then going to be followed by a power of 10, so times 10 to the. And we need to figure out what's going to go here. Well, that's going to be how many decimal places did we move our decimal point to get this, right? 2.9979 is a smaller number than what I had, so this is going to be a positive power, whatever that ends up being. All right, so let's go ahead and count it out. I moved it 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be an 8. What we're looking at here, according to the directions, is this is A and this is K. So when I write this, it's going to be 2.9979, comma 8. Okay. And then we can do the same thing here. So we need to put this in scientific notation. It is not correct, so we do need to make sure that we are putting it as one digit, our decimal point, and the rest of our digits. We're going to then do the power of 10. This number is larger than this number, so that means this has to be a negative power. Let's see how many decimal points we moved it over. 1. So that's going to be a 1. Following the directions again, this is A and this is K. So the answer is 5.1, comma, -1. All right, this one's having you do the same thing, but we are doing some addition first. So we have 4.0 times 10 to the third plus 4 times 10 to the second. We're adding those. So we do get the fact that 4400 is our answer. We want this in scientific notation. So we're going to put it in scientific notation. It's going to be one non-zero digit, the decimal point, and the rest of our digits. We don't need the zeros because they are trailing unless we needed to make sure we forced a correct number of sig figs. In this particular case, we didn't need to. We're now going to follow it by the power of 10. This number is smaller than this number, so this is a positive power. How many decimal places did we move it? Well, 1, 2, 3. So this is going to be a 3. This is A, this is K. Right. So that is something that we are looking at here. Okay. You're doing the same sort of thing here, same process. Do the math out. Go ahead and recognize what you are doing. You don't need to do it quite the way they did it. You can plug it all into your calculator. Right. This is about converting between prefixes. So we are looking at kilometers to meter, or meters to kilometers. There are 1,000 meters in 1 kilometer, right? Because kilo by definition means times 10 to the third. So if we want to convert from meters to kilometers, we can do that using a number of different methods. And the one I'm going to use right now is I'm going to use the box method that we talked about in class. Right? Anything in the top we multiply, anything in the bottom we divide. When we do that, we do get the fact that there are 24 meters in 24 kilometers in 1 meter. Excuse me. Right? This just goes in the opposite direction, right? So we're going from 85 kilometers and we want meters. So 85,000 meters. All right. Now we are looking at conversions. We have practiced conversions a lot. Just go ahead and sort of make sure that we are on the right track. So this first one, we are converting between inches and centimeters. So if we have 65.1 inches and we want it in centimeters, my centimeters is going to go in the top. My inches is going to go in the bottom. We found that conversion factor here by reading all of this stuff is 2.54 centimeters per 1 inch. So let's go ahead and do that. So 65.1 times 2.54 gives me 165.354 inches. We do only get 3 sig figs, and we are told to express it in 3 sig figs. So we're looking at this. We do not need to round up, so it's just going to be 165. All right, so then we talk about the fact that you may need to change a couple different times. So this gives us a hint. We are looking at yards, and we need to go to miles. So 5,320 yards, and we want to go to miles. We don't have a straight conversion from yards to miles, but we do have a conversion from yards to feet, and feet to miles. So if we go from yards to feet, 1 yard is equal to 3 feet. And then we're trying to go from feet to miles. We know that 1 mile is 5,280 feet. So 5,320 times 3 divided by 5,280 gives me 3.0227, and that 27 repeats. All right, and that's, let me not drop my units, that's miles. We do want our answer in 3 sig figs. So to 3 sig figs, that's going to be this. So 3.02 miles. All right, that same process is going to follow for the next several. This one's a little bit more complicated. The hints are really, really useful here, where we are looking at converting between TEPs per square meter and dollars per square yard. So our Loveling clothing maker thought he was being super cool and bought a bunch of fabric, very luscious fabric, and grossly overpaid for it. So he ended up losing money when he sold it back in New York. But we want to know, how much did he lose? Let's first of all find out how much did he actually pay. So we're given a couple different pieces of information. We're given the fact that he paid 400 TEPs per square meter. He sold for $120 per square yard. He bought 500 square meters, and we have our conversion factors. Right? So those are things that we're going to use to solve this problem. We first of all want to find out how much did he pay. Right? So he bought so we have 400 TEPs per square meter, and he bought 500 square meters. Right? Why do you think I'm doing it like this? Well, if I find out I paid this per area, and I give it an area, I'm able to find out how much I actually paid. So when I get this, I have 400 times 500. I get 200,000 TEPs. All right, so that's how much money he spent in TEPs, but that doesn't really mean a whole lot to us. So we do want to find out how much he spent in dollars. So let's go ahead and convert from TEPs to dollars. So that's going to be this conversion factor here. So we know that 0.625 dollars per 1 TEPs. All right, so we're going to multiply that by 0.625. And we get the fact that he spent $125,000 on fabric. All right, so this is how much he spent. That's the first part of this one. That gives us this hint. Okay. And the hint does take you through everything. How much did he pay in TEPs? That would be this 200,000. And then how much did he pay in dollars? Is that $125,000? We now want to look at the price in New York. Well, let's see actually how much cloth he actually bought in New York terms. We see the fact that he has 500 square meters. Well, that doesn't mean anything if the stuff in New York is in yards. Let's go ahead and convert that into yards. We do get that conversion factor that was given before, and we do use that. We get this conversion factor. You can square it like they did here. I'm going to show you just doing it twice. So we want the meters to cancel, so that's going to be in the bottom. So 0.9144 meters, 1 yard. So it is important to note that if you only do this once, this only cancels with 1. You need to do this twice. All right, this is one of the most common mistakes that I see. All right, this is the same process as what we saw in the squaring here. And we get the fact that there is 597.995 square yards. So that's not to the correct number of sig figs. We do correct that to sig figs. That's going to be 598 square yards. That would be what goes in there. So we want to know how many dollars did he actually make. So we're able to take that $120 per square yard, multiply it by that square yards we just got. And we get 71759 dollars. And this is how much he made. Right. Remember, our ultimate goal here is to find out how much money did he lose from this transaction. This is how much he was able to sell the cloth for, but this number up here is how much he spent to get it. So we need to find the difference between that. So we are looking at $120,000 minus the 71. We got 3 sig figs, so $71,800. So 120 minus 71,800, and he lost $71680. Whoops, nope, hold on. I can't type in my calculator. All right, he lost $48,200. Yikes. So that is the answer to this question. So the same sort of process is going to be what happens with the next one. So just make sure that you are paying attention to that. This one was pretty much a vocab, kilogram, how many millimeters are in 1 meter. There are more millimeters than there are, millimeters are smaller than a meter, so there are going to be a large number. So this is going to be positive millis to the third. This is a conversion between base units. Again, this is a unit conversion. Just making sure that you are paying attention to what you're doing. Those seem to be most of what we're looking at. Let's go ahead and check what are physical quantities. We can measure acceleration is a physical quantity. We can measure length, it is a physical quantity. We can measure speed, it is a physical quantity. Safety, while a great concept, not something you can physically measure. Chromaticity, which I know is a mouthful of a word, refers to how shiny something is. That is not something that is a physical quantity. We can't actually measure that. Or the fact that it is shiny. Just checking that you understand what is the rules for significant figures. Speed and velocity are have the same dimensions of length versus time and describe the rate of motion of an object. Velocity and speed are not. Both vectors are both scalars. Velocity is a vector, speed is a scalar. They do require a numerical value or a magnitude, but only velocity requires a direction. Right? So velocity is a vector, speed is a scalar. Speed does not include any information about direction of travel, but velocity does. Right? Again, some sig figs. And how many digits you get. Right? Dimensional consistency are some of the issues that I saw the most with here. Some of the things that you need to know is that speed is measured in meters per second. time is measured in seconds, and A is measured in meters per second squared. We want to know which things have this unit. So we're going to plug our units in here and see if anything matches. X, by the way, is a position, and it's measured in meters. So if we take meters per second, we square that term and divide it by meters, we get meters squared over seconds squared divided by meters, which is meters per second squared. Well, that was easy. This one has units of acceleration. Let's make sure that the other ones do too. So I have meters over seconds, and that term is squared. Wow, that also has units of acceleration. Velocity is meters per second, and we're dividing that by seconds. Well, that simplifies down to meters per second squared as well. Woo! We got another one. This last one is meters for position and seconds for time. That term is squared, so that's meters times seconds squared. So this one is not. Okay. Again, all right, so what power requires it to be dimensionally consistent? So we want both sides of our equation to match in terms of units. So we have velocity squared, so this is meters per second, and that term is squared, is equal to 2, which doesn't do anything, times A, which is meters per second squared, and we want something here. So we have meters to, I'm just going to go ahead and call it to the x, or actually, no, we'll make it p. Okay, because we need to find out what that p has to be in order to make everything match. So let's go ahead and find out what this side looks like. So we distribute that square. So I have meters squared over seconds squared. So whatever is happening over here needs to be what happens over here. I already have meters per second squared here. So whatever I multiply this by needs to give me another meters in the top so they match. Right? So just another meter matches. So that means this needs to be a power of 1. Okay? That's sort of the same process that we are going on for the rest of these, and we can go ahead and backtrack to these at another